Hello and welcome. This is Columbia Basin Research's fourth video in a multi-part series on using Program Roster. Program Roster is a program created by Columbia Basin Research at the University of Washington's School of Aquatic and Fishery Sciences. Program Roster models the life cycle of Pacific salmonids from the initiation of the juvenile migration as smolts to the end of the spawning migration as adults. In this fourth video, we will go over fitting roster and selecting the proper model. Alright, so let's focus on fitting roster and selecting the proper model. In most cases, the default model provided by roster should be sufficient to analyze the data. In some cases, however, the user may need to modify the model file to properly fit the model to the data. The following steps will assist you in formatting the model file. Begin by loading the file with all the age classes observed. Try running the default model with the value in the Extent of Transportation Effects window set to the first adult site, for example 7 if there are 6 juvenile sites. If the model in step 2 does not fit, then it may be necessary to edit the model file or the original data file. Another reason the model does not fit has more to do with the data than the model. For example, steelhead years are from July 1st to June 30th. Adult steelhead may be detected on June 29th at the first dam, then after July 1st in upriver dams, giving them a multi-year return error. Roster only does 1 year. This would have to be fixed in the tag history input file. You can save the model file as either an XML or a text document under the file menu, then open and edit the model file. For example, open your tag data file. I'm using Notepad++ here. Go to line 6588. The line indicates that the steelhead was detected in adult return years 1 and 2. Look at the first detects at each dam during the adult years. This steelhead started its upriver run 4 days before the next steelhead return year started, 1st of July to 30th June, with the rest of the upriver detections occurring after the 30th June 2020. This is a case of the wrong return year being assigned to a detection. The more appropriate year would be a B in the roster input file. The necessary edits will depend on the dataset. Some common changes are described here. Examine the parameters report, which lists the default initial values that roster uses, the MOM estimates. If any of the MOM estimates other than for the TI parameters, RIJ, are equal to 1, 0, then the default model file or the data file will need to be modified as follows. Number 1. Detection parameters PIJ, PIJC, or PIJTK, and the last reach parameters lambda JC or lambda IJTK that are very high, for example 1 or above, cannot be estimated and so must be fixed in the model file. Rather than fixing them to 1, they should be fixed to a value very close to 1, such as 0.999999. Roster uses log likelihood for estimation. A likelihood assigns a probability to all possible events, so survive and not survive. For example, log survive equals 1 is equal to 0, but also means that log non-survive equals 0 is equal to negative infinity, which is very hard to estimate. This is not a hard and fast rule, as sometimes a combination of parameters will mitigate a single parameter estimate, a greater than 1 estimate, so that the likelihood is still estimable. Number 2, survival parameters SIJ, SIJC, or SIJTK that are equal to 1 or very close to 1 may need to be fixed to 1. In general, roster can estimate these parameters, but the particular structure of the data may make this impossible. Try fitting the model both with and without these very high survival parameters fixed to 1, or 0.999999. If possible, it's preferable to leave these parameters free, not fixed, but in some cases that option may not work. Number 3. If the MOM estimate for a detection parameter is equal to 0, that means that the parameter cannot be estimated for this data set. It is not necessarily the case that there was no detection at the particular site, but may be the case that no fish detected at the site were also detected at a later site. Rather than modifying the model file, it is necessary to remove the fields corresponding to the detection site from the data file. To do this, it is necessary to run the raw Pythagoras data file through PitPro again, omitting the problematic detection site. If the problematic detection site is the first or last juvenile or adult site, then the meaning of the performance measures SJ, juvenile survival, or SA, adult survival, respectively, as well as SAR, will be altered. Number 4. If the MOM estimate for survival parameter is either 0 or INF, it is likely that the detection parameter for an adjacent site cannot be estimated. Check if a detection parameter has 0 for its MOM estimate. If so, remove the detection site from the data file by running the data through PitPro again. Reload the modified capture history file into roster and try fitting the default model again. Number 5. If the MOM estimate for a parameter is NaN, then it may be necessary to specify a numeric initial value seed for the parameter in the model file. If the model still does not fit following the edits described here, then examine the data summary report and note the sizes of the observed age classes. Age classes with very few detections will be difficult to analyze and may need to be removed. This can be done by number 1, censoring. The capture histories of fish observed in these age classes with the censoring occurring at the final juvenile site at which the fish was detected. Number 2, alternatively, the detections in the problematic age class can be recoded to fall in an adjacent age class. For example, 2 age classes are collapsed into 1. This option is not ideal because age classes cannot properly be collapsed unless there is no difference in adult upstream parameters between the 2 age classes. However, because adult detection and survival estimates are often very high, it may be logical to collapse the 2 adult age classes. Number 3, remove from the data file the capture histories of the fish detected in the problematic age class. This option is reasonable only if there are very few fish to be removed, for example 1 or 2, because it may bias results. If the model in one of the above steps fits, then it may be worthwhile to explore a more flexible model structure. Try using different detections or censoring probabilities for all transport groups, including non-transported or control fish, for the first adult site. This can be done by deleting the section of the model file that equates these parameters. Note that if any of the parameters were fixed to a particular value, for example 0 or 0.9999999, then it must be adjusted if the parameters are allowed to differ. If the model in the previous step fits, then try increasing the site identified as the extent of transportation effects. This is most easily done by selecting the default model to be used, increasing the number of extent of transportation effects window, loading the model, and then saving and editing the model as described above, if necessary. Alternatively, the expert user may alter the edited model file so that transport and non-transport groups have separate adult parameters up to the adult site that is identified as the extent of transportation effects. It may be interesting to distinguish among groups transported at different sites. It is generally not necessary for the user to pick initial value seeds for raster because raster calculates the method of moments estimates to use as seeds. However, the user may select a different seed if desired and adjust the model fit accordingly. Now let's look a little more closely at selecting our models. In most cases, models with different structures will fit the data. For example, some models may equate certain parameters that are left unique in other models. In general, the best model captures all valid differences among parameters without unnecessarily estimating separate values for parameters that are effectively equal. There are several tools that may be used to select the best model, including likelihood ratio test and Akaike's information criterion, AIC. Additionally, common sense should be used in determining whether it is really necessary to estimate unique values for a set of parameters. Likelihood ratio tests are statistical tests used to compare two models in which one model is nested within the other. The model nested in the other may be considered a special case of the more general model. More general, full model typically has more parameters than the special case, reduced model, or estimates separate values for parameters that are equated in the reduced model. The null hypothesis for an LRT is that the two models are equivalent, in which case the reduced model should be used. Program Raster provides the information necessary to form an LRT between two nested models. If Model 1 is nested within Model 2, and the user fits both Model 1 and Model 2 in raster and notes the final function value for each model, let FV1 be the log likelihood for Model 1, the reduced model, and FV2 be the function value for Model 2, the full model. Because Model 2 is more general than Model 1, FV2 is less than or equal to FV1. The LRT test statistic is x equal to 2 times, in parentheses, FV1 minus FV2, close parentheses. Define D to be the difference in the number of parameters between models 1 and 2. For a type 1 error of size alpha, compare x to chi squared with d degrees of freedom at the 1 minus alpha significance level. If x is greater than chi squared with d degrees of freedom at the 1 minus alpha significance level, then reject the null hypothesis and use the full model, Model 2. Otherwise, use the reduced model, Model 1. For example, we can estimate transportation effects for the 3 transportation sites, but where do those effects end? At the first adult site, Bonneville, or the second adult site, Lower Granite? We can fit models with either assumption by setting the extent of transportation effects to either 7 or 8 and loading and running the default model. Let the model with transportation effects ending at site 7 be Model 1 and the model with transportation effects ending at site 8 be Model 2. The difference between these two models is that Model 2, the adult detection and censoring parameters at site 7 and the last reach lambda parameters are estimated separately for transported fish and non-transported fish within each age class, while in Model 1 these parameters are equated for transported and non-transported groups. The model equating these parameters, Model 1, is the reduced model, while the model equating unique parameters for transported fish, Model 2, is the full model. The full model yields a negative log likelihood value of FE2 equals 478,537.60 with 47 parameters, and the reduced model yields a negative log likelihood value of FE1 equals 478,551.17 with 40 parameters. This gives the LRT test statistic X equals 27.14 with D equals 7 and the critical value equals 14.06714 for 0.05.
Because X is greater than the 95th percent quantile of the chi-square distribution with 7 degrees of freedom.
We reject our null hypothesis that the adult parameters are the same for transported and non-transported fish, and Model 2 should be used. Models that are not nested cannot be compared using LRTs. For example, consider comparing two models that are identical except in how they handle adult detection probabilities at the first adult site. Model 1 equates these detection probabilities across all transport groups and the non-transport group, while Model 2 specifies unique values for the transport and non-transport groups. So far, Model 1 is nested within Model 2, and model selection could be performed using an LRT. Suppose, however, the detection probability for the first age class of the non-transport group was 100%, but for the first age class of the transport fish, it was smaller, say 80%. In this case, Model 2 would need to fix the detection probability for the first age class of the non-transport group to 1, but leave the comparable parameter for transport group free. Because the parameter for the non-transport group is fixed in Model 2 but not in Model 1, Model 1 is not nested in Model 2, and model selection cannot be done via LRTs. Instead, we use the Aquatic information criterion, AIC, which is based on likelihood values and the number of parameters in each model. The AIC is not a formal test and should not be used to compare models with widely different likelihood structures, but it is a reasonable tool for model selection roster. The AIC can be used to compare nested models as well, but in general, it's better to use the LRTs in such a case. To compare models using AIC, calculate the AIC value for each model and select the model with the smaller AIC. As with the LRT, let FV1 be the roster function model for Model 1. Here, I equals 1 or 2. Also, let KI be the number of parameters estimated in Model I. The number of parameters estimated is listed near the top of the estimation report. The AIC for the model is AICI equal to 2 FVI plus 2 KI. As an example, consider the previous models. Although these models are nested, it is still possible to compare them via AIC. Model 1 has a function value of FV1 equal 478,551.17 and a K1 40 parameters with an AIC of AIC1 equal to 957,182.3. Model 2 has a function value of FV2 equals 478,537.60 with a K2 equal to 47 and AIC of AIC2 equal to 957,169.2. Because AIC2 is less than AIC1, Model 2 is favored over Model 1 as indicated by the LRT. This has been Lesson 4 on using Program Roster, in which we covered fitting roster and choosing the proper model. We hope that this video helps you get the most out of Program Roster. Again, if you have any questions or comments in regard to Program Roster, you can find the user manual at cbr.washington.edu/analysis/apps/roster and fill out our survey there as previously detailed. You can also contact Columbia Basin Research at web@cbr.washington.edu. Best of luck on your analyses, and thank you.